So hi, my name is Sharon Wood. I'm at the University of Texas at Austin. I'm pleased to welcome everyone back. We are going to have this first panel discussion about maker spaces and how you can use these spaces to really change engineering education. I think it ties in very well with the first presentation we had, because obviously rapid prototyping is one of the things that people like to do in the maker spaces. So we have three panelists with us today. Jessica in the middle is going to talk about what's happening at MIT. Robert is at the far end, talking about James Madison, and Maria is at Rice University. So what we're going to do, we want to make this a little more interactive and I wanted to try to make sure that the panelists weren't talking about the same things, so we had a lot of overlap. So I'm going to give each of the panelists 5 minutes to talk very briefly about their facilities. And then we want to talk about 6 different ways that these facilities have been integrated at their universities. After each one of these short talks, the other panelists will have the opportunity to just make a few comments to complement or say something about what's happening at theirs, so you don't hear just one perspective. So this part of the formal presentation should take about half of our allotted time, and the rest will be open for questions. So without further ado, what I'd like to do is turn over to Maria to talk about the design kitchen at Rice.
Thank you. Thank you so much. So we are called the Oshman Engineering Design Kitchen at Rice University. Everybody asks, it's named a kitchen because it was the central kitchen for the university, and then it lay fallow for a while and was a storage closet for our facilities and engineering. And then it turned into the design kitchen that I'm going to show you. This is a view from the outside on a beautiful sunset, and it doesn't always look like this, but we captured the picture. It was a lot of fun. So we are now, after being built 7 years ago, or renovated 7 years ago, and then having 2 expansions in the last 7 years, about 22,000 square feet. And it's a space for our undergraduate students at Rice to design, prototype, and deploy solutions to real-world challenges. So we have projects in just about any area you can imagine. All of our engineering departments use it. And the way we describe it is it's a facility that's there to reduce the barriers for success for our students in engineering design. So nothing that we have there actually solves their design challenges. But what it does is it makes it easy for them to very quickly try out their ideas, prototype their ideas, and test their ideas. So this is a view of prototyping workspace. We have now 76 different tables that are assigned to teams. And this is actually a picture taken during one of our collaborative capstone courses, where there are a number of different courses that meet together, and the student teams can have their meetings and meet with all of their professors as they go. So we have a machine shop, we have laser cutters and 3D printers. I don't know why this is, it's okay, no problem. We'll work with it. Laser cutters, 3D printers, sewing machines, electronics work area, printed circuit board mill. Again, tools and technologies, and the other thing I have here is supplies. Really important. Supplies are all around the room, and they're just pretty much recycled supplies from previous projects, but they're just there so that the student teams can go grab them and use them for their project. And if they need to order something in specific, then they can do that as well with their budgets. But there are a lot of materials just available right there in the room so that they don't have to say, oh, we had this great idea, but we now have to go to the hardware store. So it's taken us a little while to get to that point, but that's where we are. It's a wonderful collaborative workspace. We now have 7 different conference rooms of different sizes where teams can meet with each other. They can write their ideas on the walls. They can have practice presentations, get coached in their presenting. They can have video or audio conference calls with their meetings. So here's a work table that you can see, and these are dedicated work tables. As much as we can, we try to assign a table to a team, and it becomes their workspace for the semester or for the year. And there's a real benefit to that, because as you can imagine, if a team has to put all of this stuff that they've set up for their own project away every evening, it really does limit their forward productivity. So the ability to have a dedicated table or half a table for themselves, for their project, is really beneficial. And the other thing that it does is it creates a co-working environment, because this team is next to another team, is next to another team of students of different ages and disciplines. So not only do the students help each other, but the faculty that come and work with their teams end up getting hijacked over to work with other teams as well. So it's a really nice hub for engineering at this point. A real key for our program is that our students are working on real-world design projects, projects that come to us from community partners and industry. And the way I like to think about it as the director of the facility is that I want every student to be working on a project that they care about, because when they care about that project, they are going to dive in a way that's much more deep and authentic, and they will learn more. They will learn what they need to know to be able to solve their problem. So as much as possible, and like I said, we have at Rice 9 different undergraduate engineering disciplines, everything from statistics, computational applied math, computer science, chemical engineering, bioengineering, civil engineering, mechanical, electrical. So all of those disciplines do work in this facility. Although it may seem like a lot of what we have are building physical prototypes, we also have computational tools for those disciplines that don't build physical prototypes. We do, like many of you, an engineering design showcase at the end of the academic year. We now have about 90 teams participating in the showcase. We don't require our freshman teams to participate, but we encourage them to. And so this keeps getting bigger and bigger, and it's getting to the point now where high schools in the community are bringing their students in to see what the students are doing. Freshmen and sophomores come in to see what the upperclassmen are working on. So it's a really nice and fun event. So I want to summarize my few minutes here just by saying what we think are the key features for the Design Kitchen are real-world challenges, students working on projects that they care about, so they have an enhanced commitment to those projects. We have a great opportunity for interdisciplinary teams, and I'll talk about that in a little bit. We also have quite a bit of professional engagement, events where we bring in industry to interact with our students, as well as, of course, mentoring teams that industry is sponsoring. And essentially what we have there is tools, supplies, and equipment to reduce the barriers for our students to accomplish their engineering design tasks.
AMU, our program was first conceived in 2005. And so we first admitted our first cohort of students in 2008. So we're about a 9-year-old program right now. And I put this slide up because I think it's kind of quaint to think about next year we're going to be admitting the engineer of 2020 as freshmen. 2016. And so we're starting now to think about what our version 2 of our curriculum is going to be. But we have right now 8 semesters of design project work in our curriculum. And it starts out with students freshman year in a 101 class. In that first class, the students get the opportunity to identify problems in the community. In the second class, they have an opportunity to build out solutions to those problems. There's, in the second class, more of a design analysis feel, and in the first class, it's more of a design exploration feel. During the sophomore year, the students have a year-long project. It's 2 classes, but we're building a human-powered vehicle for a person with a disability. And we've been doing this since the sophomore year design courses first ran. The courses couple with the statics and dynamics that they're learning at the same time, but also has a pretty strong design process component. They start by meeting their client and get all the way to the end with a physical prototype that the client rides at the end of the year. We deliver a product to the person each year. We offer a single Bachelor of Science in Engineering. So our students have the ability to tailor their degree with our capstone design sequence. The students will get on a project of 4 or 5 and work with a faculty advisor for 2 years. And that's really how they can tailor their degree. It allows for a lot of interesting different types of tailored degrees in domains that are of the interest of the students. Through all of these classes, there's a strong design build element. And so we've been taking over spaces in the Health and Human Sciences building on the James Madison University campus. The spaces that we've taken over range from the 3rd floor, 4 floors up from the basement, all the way down to the basement. And so it's pretty distributed. We've got our making equipment on all the floors of the building. And so when things get hectic, the projects and the elevators jam up. And as the students are trying to move around from space to space. But this is what we've been making do with. What's interesting right now is we are starting a renovation this summer. And so next year, most of our making spaces will be in the basement of this building. So we're looking forward to that. Some of our spaces, we have a digital manufacturing studio, which is on the first floor. Because we're sort of space constrained, our spaces all serve multiple purposes. So the digital manufacturing studio is where CAD classes might be taught, product realization classes might be taught. We have our 3D printers here, our laser cutters are here, our vinyl cutters are here, our scanners are here, and CAD stations are here. The sophomore design studio is on our second floor. It's a flexible space that can transition from a conceptual design studio in the fall to a dirty working space in the spring. And all the tables are flexible, they're on wheels, they move up and down. We've got mobile whiteboards in there. The tools are locked in cabinets so we can get them out for the students when they're going to need them. It's just a very flexible space that allows the students to do the work that they need to do to make the product. Our fabrication and machining spaces are located in the basement. We have right now 2 different spaces. One is a fairly traditional machine shop, and the other is a fabrication space that has woodworking tools and basic fab equipment. These are actually fairly close to each other. There are other elements of our fabrication and machining that as we've bought equipment, we've stuffed them in rooms where we could so that we would be able to use them. More or less, we're just trying to make do with the space that we have. I think it's important, though, to point out that there's a broader campus ecosystem. There's a number of different spaces on JMU's campus. I think based on the earlier talk, the keynote, one of the more interesting spaces is the 3-space classroom, which is a general education classroom on our campus where each computer workstation is accompanied with a 3D printer. And so the students have a printer, a computer, there are scanners in the room as well. So it allows gen ed classes to come in and interface with 3D printing in the curriculum. It's a always filled class every time it's offered. There's a makerspace that's coupled with I&E activities and has rooms that can be checked out so that the students can have a space to do work, don't have to tear down issues. We've got a new X-Lab space that's opening up where we're going to be piloting some different pop-up classes, and we'll also have some workspaces where students can check out space. So.
Good morning, everyone. My name is Jessica. I am from MIT, and I'm what they call an MIT lifer. I was there for undergrad, I was there for grad school, and I'm now a staff at MIT. So I can speak later in our discussion time to questions about being a student in the makerspace, and now being a design instructor in the makerspace and thinking about how these students use the spaces. And so I'm gonna try to lay out the framework for how it all comes together so that in a discussion you can navigate the waters as it pertains to your interests. So this first logo is the Meadowbrook School. It's an independent K-8 school right outside of Boston. And they got this grant to have a makerspace. So the school is from 1923, and it's very traditional, but also very innovative and always like at the edge, one of the top independent schools in the nation. And they started with what was a computer lab, and then they put in some 3D printers, and then they got this itch for a makerspace. But they wanted, laser cutters, they wanted to do more. But they needed something that was more cohesive to integrate with the curriculum before they could sort of make that jump. I'll talk about that later. Then there's the Edgerton Center at MIT, which is sort of like the engineering education outreach hub for the MIT. We started as a support center for our MIT students, our undergrads, so we have a bunch of student shops. Many are student-run and 24-hour open access. I can speak to that. And then we started realizing that we could use these same services for the students that were in the greater Boston area and ultimately help them come into MIT as well. So now we have all these K-12 programs that I'll go into later as well. And now we have this beautiful partnership where Meadowbrook used that grant to partner with the Edgerton Center and produced me, the design thinking integration strategist. So I work in how to think about everything that we do at MIT that we do really well. How could we help this K through 8 school do it as well in their community? In the grander MIT scheme, like I said, I could speak to all of the maker spaces. I've taken most of the design and maker classes, or taught them in some capacity, and including, Neil Gershenfeld's How to Make Almost Anything, sort of the founder of Fab Labs. So I can speak to how they all interface. We have over hundreds of thousands of square feet of makerspace distributed all throughout MIT. This is just one shot of a Papalardo lab. You can imagine seeing a wall down the middle, and on the left would be this machine shop area with the lathes and the Bridgeports and the mills and everything. And that's open, 9 to 5 with our shop staff. And then over on the right, this wall that is all connected, but it's just this temporary wall, is the student space, a project space. And I think that would be a key takeaway, is always have project space and tables when you're designing the machines. Don't let, the machine to team table ratio should always be 1-to-1, I think. And so now MIT has this teaching systems lab, which came from a partnership with the Woodrow Wilson National Fellowship Foundation, and they're starting a new graduate school of education called the Woodrow Wilson Academy. That's our president, Raphael Reif, and Arthur Levine. And they're thinking about how do we redo teacher training? How do we rethink about how teachers are made? And so that's also going to be my job this year as a professional learning designer. And finally, something else that I could speak to is this education design thinking workshop, or design shop, that we coined for my master's thesis, which is only an example I give here as to how mobile these makerspaces are. So this is just a shot from the video you can see on our website of, I just took a hot wire cutter from the Papalardo lab, I borrowed it over the weekend, and took it to this bigger innovation center, this big open space, and taught people how to use a hot wire cutter in an effort to prototype their ideas. So this is some idea for how to redesign education, a play lab where administration and students play throughout the school day. But just small sort of snippets of making and how powerful they are to grander ideas, I think, is a really, really powerful thing we're playing with today. So my talk is mostly going to focus on that intersection of the Meadowbrook K-8 school and their up-and-coming makerspace, and the Edgerton Center and how that partnership has been supported. So this is my layout of, if you have to think about the spectrum of what happens in makerspaces, in sort of a gradient from tinkering to designing. It's not that one is more worthwhile than the other or less worthwhile than the other, but I think it's important to understand the purpose, the sort of intended learning outcome of your unit or of your space. A colleague of mine put it best, I think. He said, tinkering is the grammar of the makerspace. You need to know how to tinker or how to play with things, and then you could sort of move into the more cohesive, comprehensive units. And so these are some of the ways that we use our makerspace at Meadowbrook, at the K-8 school. Actually, and you should note that they don't call it a makerspace, they call it a Eureka Lab, sort of to become a little bit apart from the science techie words and encourage the history, the social sciences, the art teachers to also come in and use the space. So Eureka, this idea that you could have enabled by or facilitated by the makerspace, but really you can be in any discipline when you have that Eureka moment. So a couple of things we do in the Eureka Lab include this Make elective for the students, 5th through 8th grade students. This is one of the electives they can learn Chinese or they can learn how to make. Also an art tech class is one of the options. It's sort of like a more techy art class, since every student needs to take art. This Saturday thing started at the Edgerton Center. It's another way that what happens at MIT kind of infuses its way into the school. The Saturday thing is just an open 3 to 4 hour time on Saturdays, like 11 to 2 or something, one Saturday a month, and it's just an open lab space, open lab hours. And kids from the school and also kids from the community will come and just make. Sometimes they're learning how to work the laser cutter, sometimes they already have a project and they just need the space and the machines to keep developing it. So it's open for the community like that. Summer internships are offered to the very Meadowbrook students. So this is like middle school students and elementary school students that are working in the lab over the summer, sometimes making the build plates, for example, or one of the projects was to make the table and the shelving unit for the laser cutter so that it could all be cohesive. And that sort of starts to empower them and see the space around them as something that they can affect, something that they can modify. And finally, we provide curriculum support for the teachers. And so that's mostly what I do in helping them think of lessons that do skill building and ways to integrate different projects that they already have throughout the school year in their lesson plans, and thinking about ways that you can make it more makerspace relevant.
Perfect. So we're going to now transition into the discussion of individual items, and Jessica is going to continue.
Okay. Hi again. So I just want to point out one of the reasons that I sort of format this Makers Spaces is twofold. One is that I hope that we are designing our maker spaces so that students really understand that it's for them, it's for the maker, it's not for our needs, it's for theirs. And this idea of the paces, you know, the maker spaces are so cool because you can move at your own pace. And as individualized learners, we can understand to use the tools to serve different learning styles. And I think that's so cool to explore. So this part is about design thinking and what that means. So could you raise your hand if you sort of understand what I mean by design thinking? Kind of, you'd be able to get it if I kind of said that? Yeah, okay, great. So this is from the blog of the Department of Education, and it's teachers being frustrated, and the quote is, "Too many of our students just give up. If only they tried, they would succeed." Others say, "If students learn the habits of stick-with-itness, they can grow and feel successful." So this actually article didn't mention at all makerspaces, and it didn't mention at all design thinking, but I thought it was an interesting point of view of how people are asking for the same thing. We can just call it so many different things. So this is the way that design thinking has been sort of rebranded at Meadowbrook. And design thinking is just the process by which you engage in a problem-solving activity, and design thinking because it's something more akin to what a designer would think like going through the process. So for them at the school, it's really important to have empathy in the center. And it's cool that design thinking was sort of the cohesive narrative that really sold Meadowbrook as a school in getting that makerspace. It wasn't just that they were going to have all these machines in the corner and kids were going to sometimes use it, sometimes not, but it was that there was a cycle of reinforcement that the students were going to have machines to better understand the world around them. They were going to use technology to better help the people around them and be more empathic towards their surroundings. So an interesting pitch if you ever needed one. So I think my 3 points for this section are around cyclical reinforcement, goal alignment between design thinking and makerspaces, and thinking about design thinking as a breakdown of the making process. So cyclical reinforcement, I think there's a beautiful symbiosis happening between design thinking and makerspaces. The more if you're doing design thinking correctly, or maybe for the cooler problems, you'll go through the process and get to this prototyping stage, and, well, you can prototype with cardboard and low-res materials, certainly, but the closer you are to a product, the more you want to use the legitimate machines, right? The laser cutters and the 3D printers, and then move up to the mills and the lathes. So the more you try, the deeper you do design thinking, the more you would want to use a makerspace, I think. And these deeper levels of makerspaces, again, they show you how unique a laser cutter is as opposed to a 3D printer, and not that they're all hammers, but you start to better understand the differences in technologies, and so hopefully you're thinking more like a designer into what is adequate and what is not. My second point is around goal alignment, that really they're in many ways the same thing. Both design thinking and maker spaces cultivate students with a growth mindset, students that are empowered, that seek non-obvious solutions, that embody a hacker mindset for the world around them, that are problem finders. So more than problem solvers, they're problem finders. They're looking at the world around them critically and thinking like, I could do better. I can help this be better. And I think both design thinking and makerspaces help us want a diversity of skills and a diversity of experiences. It's so much more richer in the experience. So that's why I think design thinking is a way to make makerspaces plus or to infinity and beyond, maybe, to quote our intro slides, because it's beyond the physical artifact. It's about the tools that I'm learning in the makerspaces. I can apply that to non-physical artifacts in the world around me. And as a third point, I've seen design thinking work well for teachers that were more intimidated from, they were very intimidated from the word makerspace, but they were less intimidated from the word design thinking. And I think design thinking, because it has that 5-stage process, it gives you more entry points into the process. So it gives you more check-ins, more assessments, and it lets you know what is about to happen. If the teacher's supposed to be this knowledge curator before, and now she's supposed to be this facilitator in the classroom, and she doesn't know where the project is going to go and what direction it's going to take, Design thinking at least gives them some grounding, these 5 steps where you can probably do a check-in or a design review or something, and kind of know what to expect, as opposed to if you were just letting them wild in a makerspace and you said, go make something, they might not know what paces the students are at or where in that cycle of making they were. So very quickly, I'll go through some of the things that I do as a design thinking integration strategist and how it's sort of all nested in the middle of my work with Meadowbrook. So at the beginning of the school year, I did a boot camp, a design thinking boot camp for all the students. I taught them, basics of sketching. We played with Liz Gerber's mock-up cards, which are a great tool to get them making really quickly. I also work with the curriculum of the teachers. So we went to the Nueva Design Thinking Institute in California this summer, and we rethought from the very beginning, what is it that middle school scientists from Meadowbrook want to be like? What do we want to see in them? What are the character traits and qualities, et cetera? And that transferred into sort of curriculum mapping and what parts of the design process we want the students to go through, and all the way to like schedules. And so I help them use these tools in their classroom and how it would integrate with the makerspace. Sometimes I teach, I just jump in there. Sometimes I teach the Make Elective how to sketch, and sometimes I teach them what is the point of an interview and why would you use a laser cutter and not a 3D printer. This is the cutest picture of students testing their prototype. This is a prototype of how might we excite junior kindergartners. So this is the 6th graders designing something to excite junior kindergartners about learning about the birds on campus. And so this is like a role-playing game inside of a nest. I mean, if that doesn't break your heart, I don't know what will. I also go ahead and again, work with the Make Elective. So I taught some girls how to solder, this idea. They're like, it's not sticking, the wire, the LED is not sticking to the battery because the hot glue gun is not conductive. And I'm like, well, what if you had something like a hot glue gun that was conductive? What do you mean? There's solder. Oh my gosh. So I taught them how to solder, on Thursday, which was so fun. I love the bright green nails in there. And I document sometimes. It's about turning like the research into something that's tangible and bite-sized to use in the classroom. So this is like a quick mock-up of a poster, for the famous 8 brainstorming rules of design and design thinking and kids, which is also usable in a makerspace, right? This is just sort of the curriculum overlay in a way of what would happen in a makerspace. And then finally, we are really interested in the research that is happening as an academic at heart. And so I'll just briefly go over these 3 questions that end up being the bigger pinch points right now, which I would love your discussion around or any papers that you want to throw my way. And so the first point is this content versus construct. Teachers still feel like in order to teach design thinking or maybe teach maker technologies, they are still sacrificing some of the actual content of science or of art or of history. And so I want to be able, for me, the ideal thing would be make a whole nother class called design thinking and a whole nother class called maker time for the makerspace. But when that's not a reality, how do we convince them that this is a worthwhile skill and content base? The second one is around cognitive development, both with laser cutters and with user interviews in the design thinking process. Is there a cognitive limit to the students? Is there something that you can ask a high school student to make a user interview and draw insights, but can you ask a kindergartner? Probably not. And so where's that line in the middle? And finally, this genuine assessment. There's so much going on in makerspaces and in the design thinking process. How do we, and I know we'll talk about this later, how do we address that and how can we pick up on that while we're teaching our kids? Thank you.
This next section, I was asked to talk a little bit about projects and courses in our facility. And I'm going to preface this by saying that I obviously didn't take the timing out of my slides, but I would preface it by saying that I'm leaving a lot unsaid, and I'm hoping that if there are things you want to know more about, that you will be asking it of us. So before 2008, 2009, when we opened the Design Kitchen, most of the projects that we worked on at Rice in engineering design were in single discipline teams, not all, but most. And each department was its own little silo. So there was no sharing of tools, not for malice, but just for lack of understanding of what was available for the students. Projects often were built in teaching labs where other laboratory-based instruction was going on, so there wasn't much space, or students would take things and do this in their dorm rooms, but it wasn't really conducive to collaborative work environments. And almost all at Rice, at least for us, almost all of our design opportunities for our students were in the senior year. It was capstone, and if I want to be a little cynical, I might say it was capstone that was there because we had some requirement called accreditation that required us to do a capstone design experience. And maybe the attitude was not so great around teaching this skill, but I think it wasn't because of any sort of malice. And I will also say that the projects might have been a little bit boring because they were just repeated year after year. You know, a faculty member or two would settle on a project that they thought was a great capstone project, and they would milk it for all it was worth until it was not fun at all for either the mentor, advisor, faculty, or students, which is really no fun. So let me just give you an insight on a couple of projects now. We have a very vibrant engineering design program starting at the freshman year. We do projects with community partners like, for example, the Houston Zoo, where students are working on projects that might interface with animals at the Houston Zoo. This is a feeding device for giraffes at the Houston Zoo. We also work on devices for people with disabilities, any kind of community partner. A rule of thumb, we've gotten much better over the last 4 years that we've offered freshman design. A rule of thumb might be that a graduate student might be able to do it in a week or two. That is probably a good one-semester design project for freshmen. So we're learning what is it that are good problems for freshmen. We also have opportunities for students either through continuing courses, through independent work, to continue working on projects that they started in freshman design, or to bring to us other projects that they would like to work on. And so this is a project where students built a robotic arm for this young man who is a client at the Shriners Hospital for Children. And this ended up becoming an 8-semester project for these students. And they not only did the technical design, but they did a number of business accelerators. They got a couple of grants. They're thinking about how does this turn into a product. So it really became defining for these 3 students that stuck with the project, a defining part of their entire academic career at Rice. We also have students working on kind of other fun type things. This is a putting device to give feedback to people who are learning how to putt. And this also became an entrepreneurial effort. We also have maybe more serious projects coming from industry, valve redesign for the oil field, those kinds of projects as well, NASA-related projects. I think on our OEDK website, if you go into the oedk.rice.edu website and click on projects, I think it looks a little different than this now, you'll find a listing of about 400 projects that have been done in the last 4 or 5 years, and you can kind of see the kinds of projects that are done. They're all over the place, really. We also have additional programs that we are able to do because we have a central facility to do engineering design at Rice. One is a weekly innovation challenge. It's called Innovate. It's a project that I lifted straight from a colleague of mine at my FOEE conference that I went to a number of years ago with permission. They said it was fine for me to take the idea, and we do a weekly innovation challenge that involves not only students, but faculty and staff. So our carpenters from campus will come and work with students on these weekly challenges, and it's a really huge amount of fun. Faculty were the hardest people to get to participate, by the way. They didn't want to sit with students and staff, I guess, and build things. We have around the kitchen table dinners, which is a dinner, an opportunity for industry, alumni, and our students to get together. And we pick a topic. Maybe we'll have 5 or 6 teams. They'll present for 3 minutes each about their topic, and then they just have dinner. But it's a wonderful opportunity for professional engagement. Fabrication workshops run by students primarily, but some faculty and staff to learn how to use the tools. Summer internships, many tours for both local schools, prospective students, and industry. And then our student clubs are using the facility as well. And so where we are now with engineering design at Rice is that our students primarily in almost all disciplines are working on real-world challenges. These are real problems where there is a client or a mentor, someone who says, if you solve this problem, I would like to use your solution. So the students are really motivated. We have a huge potential for interdisciplinary projects, and I'll talk about that in my next section. We have a truly interdisciplinary environment where faculty and students and professionals, industry alumni are all engaging with each other, learning from each other, and making nice forward progress. And engineering is more real to our younger students. Our younger students have had an opportunity to work on an authentic design challenge, and now they understand why they're learning about gears and gearing ratios in their courses that come later. So they're quite motivated to learn those things. We also can push our students to go beyond the technical, do an elevator pitch competition, or think about the policy implications of the technologies they're developing. And so we're able to do that as a central facility. Engineering design has started to be woven throughout the curriculum. Again, I will talk about that a little more in my last little section. And we're now proposing a minor in engineering design for our students. So it's really taken us from almost, maybe not completely sort of dislike of the fact that we're required to do engineering design to really recognizing that this is a skill that is very beneficial for our students no matter what their discipline in engineering. Rice now, every department, all of our 9 departments, even those that are not traditional kind of engineering departments, so statistics, computational applied math, and computer science, all have a capstone design requirement now. So everybody is doing it in the School of Engineering. The last thing I didn't mention is that while our facility is there for engineering students, students that are non-engineers that are working on technology development, if they're undergraduates, are welcome to use the facility as well.
So about a year and a half ago, I had the opportunity to join, Julie Lindsay invited me to join, or JMU to join, on a NSF-funded project looking at maker spaces and the impact of maker spaces on retention and student self-efficacy and design. And we started out looking at some current best practices. And so on this project, there's 3 different universities. We have Georgia Tech, we have Texas State, and James Madison University. And we're 3 pretty distinctly different universities. One's an R1 research institution with a fairly well-established, cohesive makerspace. Texas State actually just opened their first makerspace this fall. And it is a very interesting campus with a very interesting, ethnically diverse student population. I think they rank number 13 in the country for Hispanic graduates. 45% of their students are ethnic minorities. It's a really neat population of students there that are very engaged, and their makerspace is actually housed in their education program. So it's our education building. So it's a really neat environment. And then James Madison University, we've really kind of pulled making into our curriculum. So it's very curricular for us. We have a lot of design build projects that our students do in the classes I mentioned in the design core, but also throughout. There's a lot of design build elements, even in the labs and the courses they're doing, and the technical electives and the research type courses that the students decide to take. So the 3 universities are fairly different in their approach to making. And so we first started out in this project thinking about current best practices. So the ways in which people are actually attacking maker spaces across the country. And so we went through the US News and World Report Top 100, which is like 120 some schools, and we web searched. And we tried to find universities that are advertising that they have maker spaces to figure out, if you're advertising you have a makerspace, what are you saying is your makerspace? And we started pulling out best practices that we saw that a lot of universities are saying that if they have a makerspace, this is what's in it. Ironically now, well actually ironically 3 months after the paper even went out, so before it was even presented, it was outdated because of the rapid growth in the way this is being pushed from White House initiatives, the Make Schools initiative. There are some really fantastic lists out there of what people are calling makerspaces now. Slide's missing. But one of the things that we really noticed in that process was a lot of people are really focusing on the making. So there's a lot of discussion about 3D printers. There's a lot of discussion about laser cutters, where 3D printers are probably the most listed making object out there, laser cutters being the second. There's not a lot of discussion about the working space that people are using, the tables that they're using for being able to have the creative enterprises, the very low fidelity prototyping, which is very important to making. So there's a lot of discussion about this space where we're 3D printing, but not a lot of discussion about either side of that. And we found that to be quite interesting as we were looking at those schools. So what we're doing now is we're reaching out and interviewing people who have maker spaces and talking to them about what they have. Another piece of this project is looking at design self-efficacy. So we're using an instrument that was developed and validated by Carberry et al. And published in JEE in 2010 to look at whether students' self-efficacy with respect to design changes as they interface with making and maker spaces over 4 years in an engineering curriculum. So the James Madison University study is actually being deployed through our design classes. We just finished our second deployment in Sophomore Design 1 about 2 weeks ago. So as we've been looking at what we've been collecting as data, one of the big things we've realized is there's another piece of this that we're kind of leaving out. If we're thinking about the space and we're thinking about the equipment, we're not thinking about the people and the culture that's really going on in that space. And that's I think that's so important, because you can make a room and you can put 3D printers in that room and you can put laser cutters in that room and you can have great flexible tables in that space and whiteboards and all kinds. You can even give every student swipe access to it. But it doesn't necessarily mean that the students are going to engage in that space and have a meaningful making environment in that space. And so this started to get us to ask these more complex questions about the cultural influences and factors associated with making and maker spaces. And admittedly, I'm an engineering design guy, so I don't do ethnographic studies. So luckily, we have an ethnographer on our PI team at Georgia Tech. I found a really great ethnographer to work with at James Madison University. And so we had the opportunity to send some students down to Georgia Tech. They got trained over the summer in an REU, got to go into their spaces at Georgia Tech and take field notes and make spatial diagrams of how they perceived the making spaces there. And now they're back at JMU and they're doing the same thing. And so we're able to start comparing between these two universities and start looking at what are the norms and how is the MEM making happening in these spaces. What influences culture and what influences whether students are going into and out of those spaces. And so, I'll flip back now. So I want to just conclude with, I hear a lot of discussion as I'm in telecons and talking to people about, I want to assess something. I want to assess what's going on in my spaces. But there's not a lot of asking the specific questions about what you want to know. And I think it's really important to ask that question of what is it you want to know about this space? What do you think it's doing for you on your campus? What do you think it's doing for your students? You know, maybe you have questions about the impact on students' design ability, which is something that I was really keenly interested in as a design instructor. Maybe you're interested in I&E activities, which there's a lot of interest on in our campus in particular. Maybe you think there's something with recruitment that's really important, or retention, so or multidisciplinary teaming. And so I think it's really important when you sit down to discuss, to figure out what you're going to do to assess, you need to tailor that to your specific department questions, your ABEC questions, or where is it, what you want that space to be doing. Just making that space and expecting students to come and use it as a making environment, I don't think will necessarily get us to where we need to go. And so we need to know some of these more underlying issues, and that's where I personally have been starting to try to ask questions.
So my last section was to talk about the impact on our teaching and teaching courses, so the impact of our design facility. So what I'm showing here on the graph is the number of student users of the design kitchen. So to be counted as a student user, students need to be taking a course or be in a club, have a legitimate reason for using the facility. They need to watch a safety video and pass a safety quiz and agree to our guidelines. Because once they are official users of the Design Kitchen, they have ID card access and they can go in 24/7. So it's not a painless process, actually. So I think these numbers are pretty good. But these are the numbers, and we went from having about 250 student users in the first one semester, actually it was kind of started at right December of 2008, to last academic year over 1,000 student users. So we're reaching about the limit in terms of our size, because Rice has about 35% of Rice is engineers, so we have about 1,300 engineers. So we may have a few more students that would be users, but we're getting to our limit. Over that same period of time, this graph has kind of flipped with the furthest ago year at the end, 2006 and 7, and then a year ago more recently. And so this is a busy graph, but what I want to show you is a growth in interdisciplinary teams. So in blue, you see the proportion of, and in this case, I'm just looking at 3 different departments: bioengineering, mechanical engineering, and electrical engineering. And we'd already started in 2005 trying to have interdisciplinary teams, in some cases, depending on the projects. And so if you see all the way over here, we had, by 2006, 7, 8, we had about 20% of our teams were interdisciplinary. So that's the blue. And in more recent years, it's gone up. So we've gotten closer to 40 to 50%. I think last year we were right at 50% of teams. If you look at the red bars, though, these are teams that won either state level, national level, or international level awards. And so to count as winning an award, you had to get a first, second, or third place in a national or international competition or a state level competition. So what you see here in the maroon is the proportion of teams that won awards that were interdisciplinary. So one of the things that I was very rapidly able to show my peers and the students was that it appears there's some relationship between being an interdisciplinary team and doing quite well, if winning an award is a proxy for doing quite well. Now, obviously, we didn't control for what quality of students select to be on interdisciplinary teams, or do the faculty select to have on interdisciplinary teams. So this is a little bit anecdotal, but what it does show, and it's nice information to show and motivate students to think about working on interdisciplinary teams. Once students start working on interdisciplinary teams, they're able to tackle a broader range of projects. Right? If you think about whatever your own discipline is, and you think about the kinds of projects that your own students are able to solve, so let's say it's mechanical engineering. If you find yourself having to go out and look for mechanical engineering only problems for your students, you're much more limited. Whereas if you can go out and look for real world challenges and say, we're going to put the team together that can solve that problem, you have a much broader and more interesting array of projects to work on. And it's good for our students to be exposed to those things. Another impact of having the Design Kitchen on our facility has really been on the students. So I just showed this picture. This is a student team that chose to continue working on a freshman design project for several years afterwards. They were developing a wheelchair for a mechanical wheelchair for a young man that had a disorder that meant he could do the rowing motion, but he couldn't grab the wheels and push. So basically, he was in a situation where he had a regular wheelchair that always had to be pushed, so he was not independent at all. And I showed this picture because the impact on the students of working on this project was tremendous. Now, I can pretty well guarantee that none of these students are ultimately going to be designing wheelchairs as their careers. They might, but probably not. But every single one of them independently told me they got either an internship or a job offer based on talking about this particular project that they worked on. The woman in the middle talked at her interview with an oil and gas company about how she learned that welding was really difficult, and actually understanding how the weld was going to be done needed to influence how she did her design work. That's huge, right? That is, and the companies are telling us their students, if they have never had any opportunity for hands-on, well, I mean, this team did something wrong like 5 times and kept having to take it out and start over again. They learned a lot in that process, and it's something that helps them in their future careers. So I'll finish by saying that we have, of course, sort of the focus is education and providing our students with these experiences, but there are opportunities at times for these technologies to go on beyond the campus. This is a project that was finished 5 years ago. It's a bubble CPAP device that these students developed. It's in a plastic shoebox from Target, so certainly nothing that would be able to go to the clinic. Notice this student right here, she stayed with the project. She was incredibly motivated with the project. Long story made very short. Here's a clinical trial with a much more professional looking box, but it actually has the same technology inside. They did an initial clinical trial and were able to demonstrate a 40% improvement in survival for babies with respiratory distress syndrome in a country called Malawi. And here is the product that's come off the assembly line. It's now getting scaled up countrywide in Malawi with funding from USAID. The student, Jocelyn, no longer a student, she worked for us. She went and ran the clinical trial in Malawi, and now she's the product manager with our commercial manufacturing partner in California. So while these projects often are educational exercises, I think as faculty, we need to remember that they don't have to stop there, and that this is an opportunity for our students to learn well beyond just a few specific skills in engineering design. And as faculty, we have to be comfortable with not knowing where these projects are gonna go. So like was mentioned earlier, we need to have our goals for these projects, and we need to make sure that they meet those goals, but we also need to help our students and not stand in their way of actually making something of these products. So now, what are we doing? Real world challenges. Like I mentioned earlier, our students are really committed to their projects. They don't always get complete choice, but they get some choice so that they're able to find projects that they care about a lot. I mentioned our opportunity for interdisciplinary teams, professional engagement, and having the tools, equipment, and supplies to reduce the barriers for our students to accomplish our tasks. This is a repeat slide, but I wanted to really make the point that it's all of these things together, and in some sense, none of this is about the shape of the building and where the rooms are and what 3D printers we have and what laser cutters we have. All of that is beneficial and works for our particular environment, but I think this kind of facility, however it means for your particular university, can do all of these things. And so I'm looking forward to talking to more of you about how to do this in your own sites.
To echo Maria's thoughts, at MIT we have also so many success stories of students from their freshman design classes, then getting all these kinds of grants from all over the university to keep the projects going. So maybe the tie-in is through outreach, we get to showcase those students, to showcase that work, and to show even the K through 12 community around MIT that you could do this too someday. You could, oh my gosh, we're just real kids like you. We also have curly hair. We also do cool things. You could do it too. So this part is about outreach, and the first part will be about what we offer at the Edgerton Center. Again, MIT's like outreach hub. And straight from our website, edgerton.mit.edu, throughout the school year, you can just kind of call us up, and we'll give you field trips around MIT, and this could be into a lab, and you can be like, oh my God, this girl paints her nails, and she's also working a lathe. Wow, I could do that too. And all around MIT field trips. That Saturday thing that I mentioned, that's just like open hours on Saturdays. So these are just, I put this up here because there's small ways that if you have a makerspace or any kind of space that you would like to invite K through 12 students into, it's amazing how much it'll motivate not only the K through 12 students, but we find it also motivates the undergraduates, this sort of feeling of being able to give back. And what I learned, it took me so long to learn how to solder, but now I can teach someone how to solder, and that's just so powerful to them. Suddenly that small skill becomes so capable, so capacitating for them. Teacher professional development available year-round. This science on Saturdays from the MIT Museum, which could be, you can put your undergraduate freshman advising seminar to do these things, 1 hour a week, and see what they come up with. It's amazing when we give them room to play, what they might do. And during the summer, we do this month-long engineering design workshop, and we also partner with a lot of industry, which is interesting, and they help us sponsor sponsor lots of programs for students in the area that MIT undergraduates co-teach as well, so in a way of engineering education interest. And on the online, you can see a bunch of videos. Don't let them know they're learning, I think is the fun part. And so the second part of outreach, the way that I think about it, is why these partnerships are so great. So maybe this is something to help you write a grant and get a reason for a makerspace, or a reason to continue supporting that makerspace that you already have is to partner with schools around you. So this is the part of the Meadowbrook and Edgerton Center partnership. Grants are awesome because they give you that experimentation, right? Whatever thoughts you had around makerspaces and around how to teach and what not to teach and what could be best, you can try it out with some K-12 school in the area, and almost any university collaboration is going to be a good collaboration for them, right? Usually, I find that if that school is leading the grant writing process, it's NAIS, or National Association of Independent Schools. It's usually the independent schools that are able to have a staff member to even write the grant. So if you're looking for someone to take the lead, that would be the place to probably start. But I think if you're leading it as a university and you could include public schools around the area in the grant, I think that's obviously setting yourself up for grander impact. So as part of our partnership, if you just YouTube Edgerton Center and the school Meadowbrook, it's all these videos that you can see in the ways that what we do and learn and have proven at the Edgerton Center has influenced the way that Meadowbrook has designed their school. Partnerships are awesome because you get to share your resources. When I teach the K-8 kids about how to sketch, that informs the way that I teach my seniors in mechanical engineering how to sketch. And I understand, what this 8th grader is having a hard time with, my senior is probably going to have a hard time with as well. So it's interesting to translate between the two fields, or the two spaces. And something as simple as walking into tours of the very Papalardo lab that I showed first, that's going to help influence the design of the new makerspace at Meadowbrook. And so it's all these plans, and it's the architects of the school meeting with MIT instructors and staff in engineering to understand why the soldering station should be in this room and not in that room, why the project table should be next to the machines, not on the other side of the makerspace, and whiteboards everywhere and things like this. And finally, because of the perspective that gets translated and shared, I mean, you're doing research and you have your user right there with you. So what the schools are trying to train their K-12 kids to be like in college, and what the college are trying to help the kids understand before they get there, it's like supply and demand, Pareto optimal or something. It's a wonderful symbiosis. This is from a brainstorming session that we had with the tech integration guy at the K-8 school at Meadowbrook, me and my instructor at the Edgerton Center, so an engineering instructor. And it's beautiful to see when we talk about, like, what do we want to assess in this big research arc of ours. The things are so on the ground because I've been in the classroom, and they're also so high level because we have the research experience. And it's this beautiful play of balance, of this whole systemic impact that we're gonna do beautiful things. We can think about the school environment to teacher pipeline, and we can think about the teacher to student pipeline, and it's amazing how you can see all sides of the system when you can work with your partners. So I just have this here to share the two kind of big research arcs, research pipelines that we're gonna be considering this year in our research plan. The first one is in that school to teacher interface. So how can we paint the picture of the ideal environment for design thinking integration partnerships? And this is around questions around the balance of administrative initiative and teacher autonomy. Ultimately, you want the teacher to be the one wanting to integrate design thinking, wanting to integrate the makerspaces into their curriculum, not just coming from the top down, right? How do you help teachers move towards this curricular assessment in makerspaces? When is being helpful too helpful? Sometimes it's too pushy, right? And sometimes it's it's almost, you can't spoon feed them everything because one day you're not gonna be there and you want them to be able to still want that. And so to that end, what levels of support are most effective? And the second big research question is from that teacher to student interface, which includes things like the limits of the cognitive development in design thinking and in makerspace technologies for the students. Again, can a kindergartner be using the laser cutter? I don't know to what end. Where do you draw that line? When is a makerspace a limiting or a misused tool? When are we trying to make hammers out of all the tools that we have in there? And low-res materials are just as important. So getting a student to understand when is the right time for everything, I think, is like the ultimate goal. making sure that these makerspaces aren't confounding our student assessment, right? The product-oriented assessment versus the process-oriented assessment. If we just let them wild, we'll maybe have a harder time tracking how they've moved through the makerspace, how they've chosen their trajectory through there, and navigated the space. And finally, identifying the markers. I think my teachers would love to have a way when they're designing their lesson plan, when they're designing what to tell the kids to do in the makerspace, if they could know, oh, just word it this way, or just include this thing in the lesson plan, some kind of index for what's going to make a kick-butt makerspace curriculum. I think that would be really great to advance the field.
I will start with my slide with text first this time. So I think that a culture of responsibility leads to a safe work environment. I think I was kind of trying to think about what are the 3 things or 4 things that are kind of takeaways. And I kind of came up with oversight in some form or fashion and how you're going to do it. Maintenance of records, so knowing who and when and how training was done and by who and when and those types of things. And having training of some sort are really 3 things. And then it comes to this instilling this culture where you recognize that these are important aspects in that space so that the enforcers are the users. And so there's a lot of different ways that you can do this. And I figured I'd just talk about what we're doing at JMU because I think we're hitting across all of these in a lot of different ways. Our basic training is curricular. Our students freshman year in the engineering decisions class learn to use the equipment that's in our general fabrication space. They all leave with a widget. They have to do some calculations and they cut and design and build this thing based on those calculations. They have to read some engineering schematics. They use our drill press. They use our bandsaw. There's people in there who are helping them and showing them how to use it. This is kind of a 4 or 5 students with 1 person kind of overseeing them. And then there's a general safety quiz. Sophomore year, we do mill and lathe training activities. This is one-on-one. And so we have roughly 100 sophomore students who roll through mill and lathe training and get one-on-one training for 2 hours on that piece of equipment. This does not get them access to the machine shop. It gets them entry into our apprentice program and an advanced mill lathe training activity. We build human-powered vehicles for people with disability, so I bring an expert in from a local bike shop to come in and train the students on how to use all the tools and tear down a bicycle. We've had a lot of students who want to use grinders and reciprocating saws, so I'm in process of designing the tool training for grinders and reciprocating saws and the quizzes that are going to accompany that for next semester. We also have some things that are more one-on-one or on demand. Because our students can tailor where they go with their degree when they get to their capstone, it could be that they don't ever need to use a soldering iron. And so there are students who don't ever get that training in our program. But there are other students who are using our PCB mill and soldering circuits, and so we have trainings for those equipment, and they can go and have that training, and it gets certified that they've completed that training. Our MakerBots and our Affinia printers, we have training videos on Canvas for the students to pull down, watch, and then they can be certified that they've done it. There's other ones that are more kind of one-on-one, like our vinyl cutter and our laser cutter, where we haven't had a huge demand and we haven't had to push them to a video yet, but probably could be. And so this has really been a lot of what do we need and when, and where are the students going. I think it's really important that records get maintained. This is something that for us has been a challenge, to be honest. We were keeping paper records, which is insane, but we were doing it up until last year. We transitioned everything to Canvas this last year, which is really nice because we can have the TAs, the lab managers, and the stop stewards all know who's completed what quizzes, who's completed what trainings, when it was completed, and if it needs to be updated or not. They can log into Canvas and see the status of any given student at any given time and say, no, you need to go complete this training before I can let you use this piece of equipment. And something else that's really key that we've kind of realized this year and we're starting to do a much better job at is maintaining record of who comes into the space, but not just who, why. So, okay, sure, I came into that space, but am I in there because I need to do work for design? Am I in there because I need to do work for circuits and instrumentation? Am I in there because I need to do work for a research project for a faculty member? So the students, when they come in, are now logging into the spaces and saying, these are the reasons I'm here. And so this is giving us record of what our facility use is, what our equipment use is, and helps us to make the case for having this cohesive work environment, making environment in the basement of our building that we're starting to develop this summer. And so, in a way, this was really a ground zero kind of assessment for us. What is our use of this equipment? We see a lot of people in there, but we don't have numbers really attributed to it. And so another thing that's really important is how you oversight the spaces. And I know there's a lot of different models for this. There are places where there's a faculty advisor who kind of oversees all of them, but managerial role is held by students. There are others where there is a particular staff member who is in control of the space. There are others where it's peer-peer buddy systems. And you see the gambit when you look across the country and look for maker spaces. At JMU, we actually have a little bit of all of it. The machine shop has a faculty member who oversees the space. That particular AP faculty member runs the space, runs the machinist apprentice program, where students can come in and learn to be a machinist as they're also learning to be an engineer. We have other equipment that a student must use with a faculty member at any time. That's our CNCs. We only let the CNCs be used with a faculty member while they're standing there. The 3D printing lab, the students are given swipe access once they've demonstrated that they are trained on the equipment. And so we just let them in. So the students come in and out. I would bet our MakerBots and our Affinia printers have been torn apart 1,000 times and rebuilt because they get used and broken, and the students then have to figure out how to build them and fix them. And in the 3 years we've had them, there's one torn apart probably every other week. But the students have figured out how to do that, and they're maintaining the equipment in there largely on their own. Well, the lower end printing equipment in there largely on their own. And so the other thing that I wanted to point out, I showed the landscape of the JMU campus briefly in a prior deck, and we are pretty spread out. We don't have a very cohesive method right now of how we're doing training in any given place. If someone asks, it seems right now everyone is willing to share their methods of how they're doing training, but no one knows. So if I train a student on a MakerBot, or I train them on a laser cutter in engineering and they go over to industrial design, right now they can't use the equipment over in industrial design, even though it's the exact same model bought from the exact same vendor, the exact same size laser, no difference. They can't use the two pieces of equipment because the training is recorded in two different ways. And so this is a really big challenge for us on our campus that we're trying to get our heads around. And honestly, if anyone in here has ideas, I'm open. But one thing that is going on right now that I think is really exciting and really cool is we've got this group of UIF, University Innovation Fellow students through VentureWell, and they're piloting doing pop-up classes around the use of the X Labs Makerspace. And so they're going to have these pop-up classes on laser cutting or vinyl cutting or 3D printing, and people are going to be able to come in and take that class and be trained and then be certified to use that piece of equipment. And there's other ones in there that are kind of more ad hoc. So like here you see bio-inspired design. That particular class, a faculty member in engineering said, hey, I want to do this. This could be fun. Contacted the student who's running it and got on the schedule to have this pop-up class. And so now they're advertising across campus. So I think this is a really cool and interesting model. You can tell by October 1st being the very first one we offered, we don't know exactly how this is going to play out, but there's a lot of interesting ways out there, and it's kind of a give and take. We've had to have a lot of conversations back and forth with risk management at our university about what they're willing to accept, what we're willing to do, where we want to go, and finding that common ground in the middle. And so there's no clear, easy answer because this is different at every university. But I think what's really important is having those open channels between the users who want to use the space, the people who are going to be overseeing the space, and then the risk management people who are probably coming in, doing your walkthroughs and those types of things on those spaces.